In this video, we are going to talk about grounds, and it's going to be super interesting because Hans has many different examples, practical examples, to see what will happen when you mess up with grounds or ground planes. For example, like this, what we can see on the picture. Can you describe a little bit what we see here, Hans?
Yeah, so basically this is the bottom side of a board. Let me just show you what the board looks like. So it's a transmission line going from left to right, and on the bottom layer, the ground plane, I made an obstruction. And what I'm showing here is the loss of the transmission line with different forms of that obstruction. So here the obstruction is 24 millimeters. Here I put a solder blob directly under the trace, and here I completely filled it. And what completely amazed me is that when you put a solder blob directly under the trace, it behaves exactly the same way as the full ground plane. I never tried this practically before. I knew the theory, but I expected a small difference, but there is absolutely no difference up to 4.4 gigahertz. I found this totally amazing. And here in the blue line, you see what happens if you have such an obstruction. You lose 20 decibels at 4 gigahertz, which is an insane number. That's a factor 10. So the reason I did this experiment is to show people practically why ground planes are so incredibly important in your electronic design. And you should always make a ground plane. I can guarantee you it'll save you tons of money, especially in a professional environment. If you're a hobbyist, it's just friggin' annoying, but if you're a professional, for getting to do this right is very expensive. And I've seen this live many times, and I've got a number of examples of that in this presentation.
Okay, so I'm going to translate a little bit. So basically, this graph, what we can see here, it's telling us that for some frequencies, this if there is no solid ground plane under track, this signal running through this track is going to be damaged.
Yes, definitely. Yeah.
And especially higher and higher frequency it is, more and more signal we are going to lose. And the second picture is telling us that basically the return currents are really flowing under the tracks, because you didn't have to cover whole gap. You only covered the space which is exactly under the track, and suddenly the quality of the signal is exactly or almost exactly the same as if there was like solid ground plane on whole PCB. Correct?
Exactly. Yeah. Yeah, you got that perfectly right.
Okay, let's start from beginning. So what do you have at the beginning?
So I just want to start with fundamental theory, because I think this is something really basic that many electronics engineers don't really get in such a basic way. What happens when you're making a board? Well, you're basically starting on the left with a schematic, which has ideal wires and connections. I mean, in a schematic, these things are basically superconductors without any parasitics. Now, when you turn it into a layout, these wires become pieces of copper strip, basically. And these have resistance, inductance, and capacitance with every other conductor on the board. Now, if you were to finish the layout and extract the parasitics and put those parasitics into a real schematic, then you would see a big difference between the schematic you drew and the actual schematic. Now, your job as an electronics engineer who makes layouts is to minimize this difference. And one of the places where these differences can have a really big impact is on grounding. So that's why I'm so really focused on grounding all the time.
So basically, when we make grounding as good as possible, then this extra component, there will be less and less these extra components, maybe minimum and minimum values, which are not going to influence the original schematic as much as if we do it bad way.
Exactly like that. And your ground symbols that you put on your schematic will actually be as close as possible to being a ground symbol instead of something with an impedance.
I would like to talk a little bit about this, because for example, I remember when I was starting with hardware design, I was like, yeah, but you know, all these numbers, these extra components, they are super small. Like, is really like inductance of track going to make difference? What do you think?
Yeah, well, let's assume you live in a Faraday cage. there's no interference, there's no Wi-Fi, there's no cell phones. That would already solve a huge problem because these values are small, but the interferers we're dealing with are very high frequency. And that means even though these values are small, they still have a big impact. And another thing is something I call self-interference. So let's assume you have a board with a very sensitive analog channel, like a microphone. And a few centimeters further, you have a digital processor that's running at a few hundred megahertz. And I think, okay, those two frequencies are really far apart, so they're not going to hurt each other. However, if you put a signal from a few hundred megahertz into an analog front end, it is going to demodulate it. There's no way you're going to stop that. And this way, you still get something what they call audio breakthrough, and it limits your dynamic range. So there's so many applications where you would think, a few nanoharys, that's not going to matter, but it can actually completely ruin your performance. And I think that is something that is greatly overlooked, and why a lot of people think that this whole grounding stuff is a little bit of black magic. But if you understand the frequencies you're dealing with, and everything is basically much more wideband than you think in many situations, then you understand that these small values are really a problem.
Because basically these small values will become problem for higher frequencies, correct?
Exactly, yeah. 1 nanohary is nothing at 10 kilohertz, but at a gigahertz or 5 gigahertz, it's a pretty big problem. And, you know, Wi-Fi is running at 2.5 and 5 gigahertz. So that means that, yeah, there's no suppression there anymore if you have a few nanoharys in series with your ground, for instance.
But now people may think like, yeah, but I'm not designing anything about 2.5 gigahertz. I'm designing only my microcontroller board with 10 megahertz. So do I need to care?
If you only have a microcontroller, your functionality will not be hurt, but you may be transmitting quite a lot of interference. And if you want to sell a product, then you may cross certain EMI boundaries. So if you want to qualify your product, then you could have problems, and they can be expensive because then you have to redesign your board. If you already know what the problem is and what you have to do about it, you know.
Okay. And also, I would like to point out, in many videos before, we were talking about this. Even if we are running at 10 megahertz, this is not about the frequency or crystal frequency or oscillate frequency, but also about the edges. So the edges of our signal, they are going to include also higher frequencies, not only 10 megahertz.
Oh yeah, definitely.
And so in your board, you will have also the higher frequencies. If you are not aware what is going to happen with these higher frequencies, then that's exactly what can cause the problems.
Yeah, exactly. I mean, if you have a gate that's capable of processing 400 megahertz and you put 10 kilohertz on there, it'll produce harmonics probably up to 400 megahertz basically. So yeah, there's a lot more interference than you think.
Okay, so let's move to the next slide. What do we have on the next slide?
Yeah, so this is fundamental theory that's very important to me. Because if you understand this, then you can basically solve any kind of crosstalk or impedance problem on a board. So what I want to show here is where is current running. Now, on the left top here, we have an SMA connector and a 50 ohm load, and we have one ground return path and another ground return path. Now, at very low frequencies, the current will just spread based on the resistance. So we have a path length of 1 here, that's this one. This path length is 2. So 2/3 of the current will run here and 1/3 will run here, because it's purely the DC resistance of the copper traces. Now, if we increase the frequency, something interesting happens, because then suddenly the inductance becomes important, and the inductance that you get is basically proportional to the loop size. So this small loop, or on the layout here, has a very small surface area, so a very small inductance. This large loop has a huge inductance. So what you will see at higher frequencies is that virtually no current takes this long route, but it'll all stay in this smaller loop. And you can use this when you look at your layout from a high frequency or interference point of view to understand what is going on. Because another thing is, the larger the loop is, the better it will work as an antenna. And the nasty thing about antennas is that they work two ways. So you will transmit something, but you will also be able to receive something. So depending on where this is in the circuit, it's either it's a victim or it's an aggressor, which I think are kind of nice terms to use for this.
Okay, and I would like to point out, so why we are talking about this is because this is, for example, what is difference between one layer PCB with ground which has to be routed between the pins somehow randomly, and for example, two-layer or multiple layer PCB where we could use one solid ground which is very close to the track which is routed on the top of the PCB. So that would be, for example, the case with small loop, and the one layer PCB would be the case with the large loop.
Yeah. Well, that's something that I have on the next slide actually.
Okay.
Because the perfect solution for this is to use a ground plane, and then you can. I drew ground symbols here because that's what you generally do, and it's actually a close representation to reality because you have ground available everywhere. You don't need a track because you have a plane. So it's drawn here in blue is the bottom layer with the ground plane, and red is the top layer. And there's a ground via right here at this 50 ohm track. Now, if you remember the presentation we started with, that ground current, return current always stays under the track, then what you've done basically here, you have offered the current the shortest possible path in each possible condition, because the ground current will go through this via, immediately go back to the trace and go back under the trace, basically creating the smallest possible loop. And the reason that it follows the smallest possible loop is that any inductance is basically resistance, and current will always follow the path of least resistance. So this is the absolute magic of using ground planes. You really create an incredibly good ground because you're offering the shortest possible lowest impedance path that you can offer.
Okay, again, we would like to point out we are talking about AC. DC is different.
Yeah, so you have to be at a higher frequency. At DC, this doesn't work. It will still take a short path, of course, because that's the lowest resistance. But with increasing frequency, this will get worse and worse, as you can see here at this remark here.
Yeah. Okay.
Yeah.
So next.
Another thing that's good to realize is just some rules of thumb for impedance. So if you have a thin trace, a very rough rule of thumb is that it has an inductance of 1 nanohenry per millimeter. And the wider the trace is, the lower the DC.
That's 40 mils, I think, correct?
Yes, that would be 40 mils, I think, yes. Now, the wider the trace, the lower the resistance will be. That's logical. You have more copper surface area, so yeah, more conductive material. But the inductance also goes down. And so if you talk about a plane on a board, that is basically the lowest possible inductance you can make on that board, because the plane covers the whole board. And the wider a trace is, you could see a plane as a wide trace, the lower your inductance. So that's why planes are so incredibly useful to use as a ground, because the whole idea of ground is that it has the same potential everywhere on your board. And this is simply the best way to realize this.
Okay.
So let's see what's next.
Don't skip number 6. We can go back to the example what we were talking about at the beginning. So now everyone will understand exactly.
Yes. Yeah, so yeah, it's kind of nice what happens. So the forward current, so this is a network analyzer. You can basically, if you don't know what it is, it basically, in this setup, it measures the gain from this port. It measures the gain from this port to that port. So signal travels here, goes through the microwave transmission line, and then goes to the receiving port of the network analyzer. Now the return current is going to travel through the ground plane the other way. But what happens if this ground current wants to return? It hits this obstruction here in the ground, and it has to go around. Now this is exactly symmetrical. So if I did a really good job making it symmetrical, half of it will go on the top side, half of it will go on the bottom side. Now a few things are happening. The first thing, you create a longer path. Now longer paths, we just saw that, means loops, means inductance. The second thing is it'll start to resonate at some point, which you saw at that big dip at 4 gigahertz. this means you've basically built a slot antenna here. This is a general way, a given way of building an antenna. So this thing will transmit and receive at 4 gigahertz. So you lose a lot of signal. You made a transmitter, you made a receiver, so you basically screwed up your signal.
Mm-hmm. And everything what you did, you basically broke the ground plane which is under the track.
Yeah, you can see it here. I put a trace in. I put a line in which was not part of the net list. So yeah, the PCB package made a cutout around it, and I removed the varnish, or what's it called, the mask.
Mask. Mm-hmm.
So I could cover it with solder if I wanted to do that. Mm-hmm. And yeah, then I was really surprised when I made this tiny little blob here under the trace that it exactly did the same thing as a full plane, really proving that return currents stay directly under their trace.
Mm-hmm. Okay, let's go back. Let's go back to the previous one. I would like to just clarify again. So what we are looking at is basically a track, and we are sending signal from one side. We are receiving the signal on the other side. Track is routed on top layer, and on the bottom layer, instead of having nice solid ground plane, in the middle under the track we have this cut.
Yeah.
And that's why and then during experiment we will kind of remove this obstacle and we will see what is the difference.
Exactly.
So for us, if there is the obstacle, it's really bad. Okay, let's go on the next page. Why it is really bad. So on this graph, again, what we can see on this graph is the comparison of the what is you say like it's comparison between the signal strength which is sent to the track and which is received. So ideally there should be no loss. Ideally we should receive exactly the same signal what we sent out. But if there is this obstacle, if there is this cut in the middle of the PCB, the blue line will happen. For higher frequencies, suddenly we start losing the signal, a lot of signal. Minus 20 decibel is a lot of signals. And basically this signal will then change to radiation or something.
Yep.
Oh, okay. I understood correctly.
Yeah. You know, what's interesting to mention is that when people design boards, this is what I found, is that they care about the signal trace, but they forget about the return current.
Exactly. Same. I've seen exactly same.
Yeah. And that's why this is such an... Yeah, I love this result when I saw it, because I thought this is the perfect demonstration. And it's very funny, when I put this on my YouTube channel, it was actually my first movie. I had a lot of comments of people who said, now I finally have something to tell my colleagues that they have to use a ground plane. It was actually not one person, it was a whole bunch of them. So that was so funny.
Yeah, and I love the middle picture because many people, they don't know that signal return currents really flow under the track. So I really like it.
But look at the difference at 4.4 gigahertz. I mean, that's a hundredth of a dB. What's also interesting to note is that you lose about 1.7 dBs here, I think. That's because we're using cheap FR4 material. So yeah, that loss is actually... I calculated that as well for my movie, and it was exactly on top of the measure of the calculation. That was extreme luck. It was in a hundredth of a dB almost. Which is pure luck, but it shows that actually FR4 is relatively predictable in the sense of loss. Which
can we be a little bit more specific? Can we say, like, if the signal on the input is 1 volt, and if we lose 20 decibels, what is going to be on the output? What kind of signal?
0.1 volts, 20 dB is a factor of 10, so you lose a factor of 10 on your signal, which is, of course, insane. And you wonder, where did that energy go? Well, it literally went into the air.
Okay, so on the output there will be only 0.1 volt.
Yeah. So the other 0.9 volt went into the electromagnetic space and probably was warming you up a little bit in the meantime. I don't know.
Okay, perfect. Let's go and let's move to the next one. Oh, no, number 8. I'm curious. What is number 8?
Yeah. Sorry, I went too quick. Yeah, so you see on the left bottom, you see two pictures here. Now, I had ground on the top, but this ground was completely floating. So actually, it wasn't ground. It's basically floating copper plane. So I could also rip it off, and that you see that here. And now the question is, what's the impact of having loose copper on the top? Well, it's pretty big. You can see this first dip here at, I think it's 700 megahertz. The scale is in billion. I hadn't fixed that yet in my first movie.
I noticed before, yeah, but it's gigahertz, yeah, correct?
Yeah, it's gigahertz, so it's 0.7 gigahertz here. And so what's happening here, the current is traveling along this trace. There's a capacitance between the trace and this loose plane. And it starts inducing a current in this plane. And this current is starting to travel along this piece of copper, gets to the end, bounces back. So that causes a resonance. Again, starts to work like an antenna. And here you see that the first resonance is occurring at 700 megahertz. Now, if I rip off that copper, then you see that there's no resonance left. You see all these red lines are all different resonance modes on this piece of copper, this piece of copper, on this length, on this length. There are all kinds of ways that the signal can form a standing wave pattern on these loose planes, and they will. And each one of these dips basically shows one of the standing wave pattern frequencies that can occur on these two loose planes. So this basically shows that it's really important to either remove it or connect it to ground. And a little bit later in the presentation, I'll show what kind of distance you would need to put vias in order to prevent this kind of thing up to a certain frequency.
And I would like to point out this because there are always many questions about if people should do copper pour, because this is basically copper pour, okay? Copper pour, it means fill out empty spaces with copper. So first, if you do that, you should definitely connect it to ground. But if you don't do that, you are not going to do anything wrong if you have solid ground plane on the layer below the traces. So if you don't have like a very specific reason why you should do it, then I guess it's better don't do copper filling. Yeah.
It's also I like it in a way because I very often like to get rid of heat, and this extra copper just gets rid of a little bit of extra heat. But then you have to be careful that you ground it well enough, especially in the area of signal trace. If you have no signal traces in the area, then it doesn't matter because it won't get hit by a signal, so it won't form a standing wave either. However, I can imagine, I never did something like this, but if you're making a motherboard with 16 layers and you have 16 layers of loose copper and you have to make sure that that's all connected, well, that would be total hell. So then I would say better not use that pour. Or I understand that this is something that I want to try once just to prove it, is a hatched pattern, because that apparently doesn't resonate at all. And it still takes care of the copper balance in your board, which is also nice to have.
Can we jump to the pages where you actually stitch the copper?
Yeah, just a second.
Here, yeah.
Yeah, so what you see here is the exact same layout. This is the exact same trace, just zoomed in. So what this shows is the yellow trace means that the yellow vias are placed there. So these yellow points are ground points. That's where the top copper is connected. This loose top copper is connected to the ground plane on the bottom layer. And what you see, if you use this yellow connections, then you're still at 700 megahertz. Now, for the first time that something starts to resonate. If I add these two purple ones, you see that it suddenly goes up to double the frequency, 1.4 gigahertz. And that's no coincidence because I'm halving the distance between the vias. So half the distance means double the frequency. Now we can take this further. Now the yellow trace is the yellow via positions and the purple trace is added extra in the middle. So you can see that the 1.4 gigahertz now goes to 2.8, which is again double. So it's this perfectly shows the wave theory. The way you could look at it, if a wave fits between those vias, then it will get on the plane. And what I did in my video presentation is I made a table. There's actually an error in there. I calculated the speed on the board wrong. Nasty thing about YouTube, you can't correct. But anyway, the formula in there is luckily right. But you can calculate exactly at which frequency the wave starts to be able to get between the vias. And I've got that rule here. So generally on FR4, the speed is 1.5 to the power of 8 meters per second. And the general rule of thumb is if you put the vias a quarter wavelength apart or smaller, then you will be out of trouble. So you can calculate the distance like this, 0.25 times 1.5 e to the power of 8 divided by the maximum frequency. So if you want something to be problem-free up to 1 gigahertz, you fill in 1 gigahertz here and you get the max via distance in meters. Now for digital signals, what Robert already mentioned, you're always dealing with the higher harmonics. So yeah, depending on how fast your digital stuff is, you want at least 9 times higher than the highest signal frequency that you have on your board to be sure that you're also dealing with the 9th harmonic. And this is a pretty safe rule. If you do this, then you will probably be well on the safe side. But it's good to realize this.
Can we go back one slide? Because I just would like to point out that the distances between the vias are actually in the title of the graph. Yeah, just to be specific.
Yes.
Like 22 millimeters between the vias. Purple.
Yeah.
Okay.
And then you get to 2.8 gigahertz.
Okay, 22 millimeters. That's like almost like what, 1 inch? 1 inch is 25. I think.
Yeah. That would be an inch. Yeah.
Yeah. Okay. Okay. Let's go back to the beginning, and let's have a look.
Let's see. Where were we? Oh yeah, here.
Okay.
Yeah. So I made a demonstration board where I wanted to show what the impact of these ground rules is on a 9th order elliptical filter. Now, a 9th order elliptical filter is an extremely steep filter. They call it a brick wall filter. So at one point you have gain, and a few hertz further you have no gain, basically. Now, it's a funny story. This is the first project I ran into when I started working professionally, and this was immediately the worst circuit I could find for ground sensitivity and crosstalk sensitivity. So I learned all these critical things in the first few months of my career, which is why I spent the rest of my career correcting problems from colleagues who didn't have the luck of having this experience, because it's basically luck. So this is great for demonstration purposes. Now, this is basically the filter. So the signal enters here, it's a 50 ohm filter, and the signal exits here. The bandwidth is roughly 30 megahertz. And you see all these taps to ground, which short the signal in stages. And you see a number of parallel resonators. Now, each parallel resonator at its resonance frequency will block the signal. So you get a whole bunch of frequencies at which the signal is blocked. And the rest of these capacitors take care of an overall suppression characteristic. So here we can see a first set of measurements. Now, let me just first clarify this picture. So the purple line is the ideal simulation. So that uses components with infinite Q, no losses in the traces, everything is perfect.
So basically schematic simulation.
Yeah, schematic simulation with ideal parts. It's exactly this schematic that you see here. With a 50 ohm load and a 50 ohm source impedance.
But then we add PCB.
Yeah. So in this test board, I wanted to demonstrate what the effect of a PCB design is on such a circuit. So I made the worst possible PCB design I could think of. So this is the ground, which is a really thin line. We just talked about, thin lines have a 1 nanohenry inductance per millimeter. So there's lots of inductance here. And what you get is this red line.
So basically there is no ground plane, nothing.
No, there's no ground plane.
Is track, and that's
it. Yes. You see blue here, so there is ground on the bottom, but you see I went through some trouble to completely disconnect it. So it is there, but it basically doesn't do anything. I think if you remove it, it would change the response a little bit, but probably not that much, because this was 1.6 millimeters. So But anyway, you see this red line. Now, just to explain, this blue line is what I managed to do with the best possible layout that I was capable of making. So what I'm going to show here is different stages of layout, improving it every step and explaining why it is an improvement and what kind of mechanisms are basically ruining the performance.
Again, I would like to point out, so the filter works at the beginning, yeah? When you have a look on 0, yeah.
Yeah, it's a low pass.
Yeah, so it will pass up to, I don't know what.
30 megahertz.
30 megahertz. And then it's supposed to go very sharply down. But if the layout is wrong, actually for some frequencies, it will not work.
Yeah, actually, you can see it dropping down, but then it immediately stops working. At least it starts deviating from this ideal simulation a lot. And this is what I meant at the beginning. You make an ideal schematic, and then you make a board, and that adds a lot of unwanted components, which in this case cause the suppression to be really bad. Look here, we only have 10 decibels. At 750 megahertz, where the good design is close to 100. So you lose 90 decibels of dynamic range.
Just because of wrong layout.
Because of ground layout, which is insane. That's a factor of 30,000 in voltage. Just because you didn't know that ground is important.
Okay, so what is the better layout?
Yeah, so the next step is, okay, let's give each, let's use a ground plane. That's the blue plane. You can see the vias here connecting the ground with SMA connector, and you see that each of these ground connections has its own via. And then you get the yellow trace.
No, I was expecting it would be a little bit better.
Yes, this puzzled me as well. Because we're still very far away from from the 4-layer. Now, a number of things are going on. This took me a few hours to figure out actually what is going on. And it turns out there's two things. These are air inductors. So their fields run like this around it. And they are so close together that they're talking to each other. So this inductor, which is supposed to be not communicating at all with this one, is actually working like a lousy transformer. But you only need a lousy transformer to completely ruin a 100 dB suppression filter, because that's a factor of 100,000. So if you have, it's 100 decibels. So if you have minus 60 dBs of coupling, which is already a very good number, you're completely screwing your filter performance. But when I was investigating this, I found something else. I wanted to get to the root cause. So I basically removed these right 3 sections and just looked at the response with these 3 parts: this capacitor, this inductor, and that capacitor. And I compared it to the simulation, and there was a perfect correlation. So I thought, okay, that part works. Then I placed this capacitor, and it suddenly started deviating like crazy from the simulation. I mean, talking huge difference. So I thought, what the heck is going on? The current comes through here, goes through this capacitor, goes to this via to the bottom layer, goes back under there, and under the trace and back to the ground. Forward current, return current. However, the same thing happens here. Current goes here, goes through this capacitor, comes back like this. Now you have a loop here, an electromagnetic loop or an inductor. Basically, you're creating a parasitic inductor. And you also have one here. And these loops are directly looking at each other. The fields are in each other's way. They see each other's fields. So they start talking with each other. And it's quite surprising. That really ruins it. Even though these are very small structures, and you would think, yeah, it's 1.6 millimeters high. This is just 2 millimeters. How can it do anything? But if you try to make 100 decibels of suppression up to a gigahertz, this is totally dominant. So what I also tried is I tried to connect these. As you can see, I could connect these loose patches because I wanted to prove that this also has an effect. Effect wasn't that big.
So basically you made one bigger plane on the top. You connected everything.
Yeah,
okay.
It was the inductive coupling, the electromagnetic coupling due to the return currents that was really dominating the problems here. Just have to touch my camera, otherwise it turns off after 30 minutes. Okay, so now how can we improve this? Well, very simple. If you have electromagnetic coupling, then you just have to take these things apart, right? So this is a 2-layer, and I took these resonators apart and I rotated them 90 degrees. So all the fields that you create now are perpendicular to each other. So there's no loops looking directly at other loops anymore. And what you can see is, especially above 400 megahertz, you get a very big improvement. So this basically proves that this strategy works. Now, let's see let me see what the next picture is. Yeah, so what can we do to improve this? There still are relatively big loops, and the reason is this board material is 1.6 millimeter thick, and it's a 2-layer. So if the current has to travel to the ground plane, it has to go down 1.6 millimeters and follow the trace of the forward path. That still creates a big loop. Now, if we look at layer stack-ups, at the bottom, you basically see the stack-up that we use with this filter up till now for the 2-layer. So this is that long path. However, if you go to a 4-layer stack-up and you put the ground on inner 1, this distance is on the boards that I used for my 4-layer only 200 micron. So that's 0.2 millimeters instead of 1.6. Now, if you look at the inductance of a via, which is also a thing, a via has an inductance. And what you see here on the right is the inductance versus via length. So if you have a 1.6 millimeter board thickness, you get to 500 picohenries. While at 0.2 millimeters board thickness, which is basically this, it's not the board thickness, but it's the thickness of this dielectric, I think this number was 12 picohenries.
Oh, it says 0.38 millimeter.
Yeah, that's wrong. That's on the that's the supplier that I used to use. They had 0.38, but the supplier I use now has 0.19 as standard.
Okay.
So this is an error. So I actually wanted to prove that. So what I did is I made a small trace on a 4-layer board with a via in the middle, and I made the same trace on a 2-layer. This is both of these pictures are actually a 4-layer board, but on this board I use inner 1 as ground, and on this board I use the bottom layer as ground. So basically this is the schematic. Now what you expect based on this schematic is no signal coming out because yeah, it's grounded. Of course, in reality, there's a via inductance here. And this is the transfer function when you try to put a 50 ohm signal in here and measure what comes out here in a 50 ohm load. And you see the huge difference. So at 500 megahertz, it's minus 25 decibels with the 2-layer via, and it's minus 65 with the 4-layer via. So you basically gained 100 times of suppression by just improving your board technology. So if you're making high dynamic range RF stuff, this is the easiest way you could gain a lot of performance.
I would like to clarify. So basically,
yes.
What this connection what you have here, for DC, it will show nothing, yeah, because there is short circuit. But
You're
for
correct.
higher frequencies, they will actually go through, even the trace is actually grounded.
Yes.
But
yes.
it's not really grounded because there is inductor. There is no like direct short circuit, there is inductor. And this inductor is the value of the inductor depends how far the layers are. For 2-layer, inductor is going to be higher.
Yeah,
for
that's this graph.
4-layer is going to be lower. Yeah. And just this via will make this difference that in 2-layer PCB more signal will actually go through.
Yes, because your short is not as ideal as you expected.
Yeah, for higher frequencies. More signal for higher frequencies will go through.
Yeah.
Oh, wow.
Yeah, that's funny. At DC, you can actually solve this. At RF, you can also solve it. Just put enough current in, you'll blow out the via, and you solve the problem. Yeah, that would be something for, what's the name of this guy? This Iranian guy that always explodes electronics on YouTube.
Electro Boom? I don't know.
Yeah, Electro Boom.
Yeah, but this is very interesting. This is very interesting example. I would never thought about doing something like this.
No, me neither. But I was thinking about, making an instructional YouTube channel and what could I show that really brings this home. So I never did this before either. And of course, I always use this knowledge, but I never actually measured it. So yeah, for me, it was also very nice to actually do this and see what happens.
Again, this shows how important are vias in PCB.
Yeah. Yeah, so one nice thing you could do if you say, okay, with the 4-layer, a via has 12 picohenries in my case, because it's 200 microns of dielectric distance. If you cluster 4 of them together, then you would get a quarter of that, which would be 3 picohenries. So you could make a big improvement by clustering a bunch of vias together and thereby reducing the inductance. You're also reducing the DC resistance by a factor of 4, of course. But for high frequency, the inductance would be the biggest difference. And you should be able to, in theory, gain another 12 dB here. Let me see, you go from 3 to, 4 times more. Yeah, it should be 12 dB if it follows exactly these rules.
Okay, and this is I think this is very important to understand, and it shows also a lot of things for power delivery, because power delivery, a lot of power goes through vias, and this can actually play big role in power delivery.
Yeah, if you're making something like an FPGA board, for instance, and you use a single via to get the power in, and the thing with these FPGAs is they have a core voltage of 1 volt, but they might be burning 10 watts. So that's 10 amps. And then this via can cause so much drop that the FPGA stops working because all the timing is off, because the power supply has dropped too much. And you really have to be careful when you do things like this. And watch what you're doing.
Okay, and then also if you add capacitors and you have already there some inductors, it can resonate on all kind of different frequencies.
Yeah. If you start looking at power supply decoupling and filtering, you open a whole other can of worms.
Okay, let's move to the next slide. I don't want to confuse everyone now, but I find it interesting because I've done so many videos about power delivery, and we always stress how important the vias are in power delivery. So this was very nice example to actually show very simple difference between via in 2-layer going from top to bottom, and via going only between layer 1 and layer 2.
Yes. Huge difference. Yeah. Yeah, so now we can utilize this on our filter. So this is the exact same layout as the 2-layer. I copied it 1-to-1, so there's no difference. But the only difference is that the ground plane is now 200 microns beneath the top layer. And look at what we get. We get the blue response. So look at this. We went from a layout that's basically made by someone who's never made a board before, and you end up in the red line.
Connecting pins. I call it connecting pins.
Connecting pins. Yeah, exactly. Yeah, you just connect the pins. And someone who knows a few simple rules, because that we'll get to later, if you just follow 3 extremely simple rules, you're pretty much guaranteed to prevent all these problems. That's why I'm saying you can save tens of thousands of euros in the professional environment easily in a few years if you follow these rules. So you go from red to blue, which is amazing.
And you know what is sometimes what I think is very sad, that many people they insist on making 2-layer PCBs, and 4-layer PCBs now they are cheap.
Oh yes.
There is absolutely no reason why people should use 2-layer PCBs for, okay, if they manufacture millions, okay,
yeah,
you have to optimize. If you are making prototype board for yourself, or if it's hundreds or even 1,000 or maybe 10,000 of units, there is absolutely no problem. Go for 4-layer.
No, exactly. Yeah. It's in the last few years, prices have dropped so much, especially with the Chinese suppliers. It's amazing. Yeah.
Okay.
Shall we move to the next chapter?
Yeah.
Yeah, so this is actually, if you want to take anything from this presentation, this is the money maker. Really. This is 3 simple rules, and I guarantee you, based on what I've seen in 30 years, and I'm going to show examples in a moment, this is going to save you a lot of headaches and a lot of time and a lot of money if you're professional. So this is it. First, make a full ground plane. Well, I think we've been very clear on that and demonstrated how important that is.
I'm going to interrupt you.
Yes.
Now, some people will be like, yeah, but I have these analog components. I have to split it because But I think we are going to talk about this a little bit later.
Yeah, we'll get to that. We'll get to that. I have some very nice examples of why that goes wrong.
But still, this first rule is valid even for if for mixed design, analog, digital, it's still valid. Okay.
It's valid for any electronic design you make.
Number two.
Give each ground pin, so I'm talking about IC pins or whatever ground connection, connector grounds, any ground connection you have, capacitors, give it its own via.
You know how many people, I make these tutorial videos on YouTube, and I'm getting so many comments like, do you need to really place via for each pin? I'm like, just do it.
Yeah, and I'll demonstrate why in a moment, because as I said, I've got some actual real world examples. And the reason why you do it is you have no chance of crosstalk due to that. And the third one is we already demonstrate that one as well. Stitch floating planes often enough. We just gave the rules because it stops unwanted standing waves, which ruin your performance, which you don't want. So let's go to the next block.
Practical examples.
Practical examples. So this was really funny. I was working for a company that was building or designing car radio ICs, high performance car radio ICs. And these guys had spent already some time with this board. It was a single layer board. On the bottom side, there was a car radio IC. And they couldn't get the sensitivity right. They had lots of sensitivity problems. So I got this board in the lab and I immediately saw, there's no ground plane. So in order to prove that that's the problem, I cut this copper tape. So kindergarten came in very useful, cutting and stitching. And I connected it in a number of locations. And now let's have a look at the impact of that. So I've got to clarify this a little bit. On the x-axis, you see the FM frequency. It moves from 76 megahertz to 90 megahertz. You're maybe wondering, 76, that's not used in Europe? No, that's the Japan band. On the y-axis, you see this audio signal to noise ratio coming out of the IC. So you apply a modulated signal, an FM modulated signal to the IC, a few decibels above the sensitivity limit, and you sweep it from 76 to 90 megahertz, and you look at the audio SINET, the signal to noise ratio from the audio signal coming out. Now, without that copper tape, you get these red responses, and you see lots of places like here where the SINET is basically zero, and here,
so
and here, and here.
Low is bad, very bad.
Low is bad, yeah. And just by adding this copper tape, almost all of them are gone. This is the worst one. So we went from well, this is 2 or 3 to 24, and that's only in one location instead of all over the place. So this is another way to hammer home, use a ground plane. You have no excuse anymore. So you can go further than that. After that, I also designed this board, which is an actual 2-layer, and you can actually see it. Wait a second, that's the wrong one. You can actually see it gets even better. So this was with the copper tape, and this was the actual real 2-layer board. So yeah, I think that's an extremely powerful demonstration of ground planes in a high dynamic range analog environment.
How did you do the copper tape? You just cut the shape and stick it on the PCB?
Yeah. What's good to realize is where did this interference come from? Well, this radio had an analog front end and a digital back end. So it had clocks. And what you're basically seeing here is all kinds of locations where harmonics from these clocks. Look, this one falls exactly on 78 megahertz. This one exactly on 76.
Oh, you are right. It looks like exactly
84.
Periodic.
Yeah, it's periodic. And so these are basically the harmonics from clocks, which are transmitted all over the place because there's no ground. So there's no reference. There's no 0 point anywhere in the circuit. So basically everything is moving with respect to everything else all the time on the board. And that simply gets into your RF input and ruins your audio performance. So here you see a whole lot of things happening at the same time. You see harmonics, you see lack of grounding, and therefore interference. All these antennas I talked about, you're creating all kinds of antennas everywhere, transmitting and receiving antennas, and they're doing their thing and basically ruining the performance.
And the antennas are basically the pieces of tracks?
Yeah, pieces of tracks. Yeah. And the unwanted loops that you're creating. Because large loops, because there's no ground, so the loops will always be much larger than when you had a ground plane, basically. So we have another example here. This is another FM radio IC. Actually, this wasn't a car radio IC. This was an IC for a mobile phone. And well, this is a very schematic way of the IC. It had an RF front end, it had a digital part and a PLL part. Now, the IC designers, they realized that these grounds needed to be separated. But on the board design, here you see these ground connections, these 3 ground pins, and they have 1 via. So this resulted in a 90 microvolt sensitivity on a clock harmonic. And a clock harmonic is a harmonic of the digital, one of the clocks in the digital. However, on other frequencies, you had 8 microvolts, which was basically the expected sensitivity. Now, why did this happen? It's because that single via has an impedance, it has an inductance. So if there is digital current, ground current, it'll go through this via, cause a small voltage, and that'll then basically also go into the front end. Because the front end gets a signal which is connected to ground on one side and RF on the other side. So there is a voltage difference between the ground the front end gets from the input and the ground it gets from, well, from its ground pin, because this inductance is there. So the solution is, of course, very simple. Just make 3 separate vias, and then the schematic would be like this. So the via inductances are still there, but they're not.
It's not influenced by the other pins.
Exactly. So, and that basically solved the problem. And the thing is, and that's kept striking me during my career, that these were not really dumb people. I mean, these were really smart engineers, but this grounding is such a bit of black magic that this goes wrong. This went wrong very often. And the solution is very simple. So this was a violation of the rule, give each pin its own via. So Robert, next time you get another comment, send them to this one.
Yeah, I was exactly thinking about this. Like when people ask about this, I will send them to this video. Because usually I try to explain it very simply. If you use 1 via, all the currents are going to mix in this 1 via for all the pins which are connected through this via. And you don't want to do that, because you don't want other pins influence, or you don't want to influence each pin with each other. So just put separate via for every single pin. Of course, it's not always possible. Sometimes you have to connect 2 or maybe 3 pins together, but you still need to know what you are doing.
Yeah, sometimes I mean, if you're making something again like an FPGA board, sometimes you're so limited in space, and then you have to make a conscious decision like, okay, I have 3 digital ground pins. Can I put them together in 1 via? Well, in that case, there's not so much damage because they're all
same.
You're not connecting a very high dynamic range ground to a digital ground. That's a disaster. So that's why it's always good to understand the theory behind this, because then you can make a conscious, educated decision on what is best. If it gets really hard in layout, you can decide what the best trade-off is.
Yeah, but in many cases, there is enough space to place via for every single power pin.
I virtually never had that problem, actually. It's I guess motherboards would be a place where you could...
Motherboards are quite large. I think the worst what I was designing are usually computers and modules, which they have to be as small as possible. And that's what is like super difficult. Like once I was designing computer on module, and I placed their one last via, and there was no space for anything else.
Oops. But, yeah, I guess if you talk
about... I finished it. It was okay. But of course, it was not the first try. On the way, I was like, I need to place three more vias, and there is no space. I had to delete half of the layout and do it again.
Yeah, I can imagine when you're building something like a Bluetooth in-ear headset, that, you can easily run into things like this.
Okay,
So let's go to the next example. This is another real life example. I don't have any pictures of the real thing anymore. This was a car kit. Now, these car kits had something that they called a gooseneck. They don't exist anymore, but it looks like a shower hose. And at the end, there's a microphone. So you could, I guess you could pull it towards you in the car. And this was 20 years ago. So they were doing audio breakthrough testing on these things. And this is one of the compliance things that you have to comply with if you build a car kit. So you place this whole car kit with the long wire and the microwave in a cage, and this cage holds very strong electromagnetic radiation that is very heavily AM modulated. So basically you turn on RF power and you turn it off. It is almost 100% modulation that they use for this. So it's really almost turning on and off. Now that gives problems because if that gets into your analog electronics, it will demodulate. AM, if you put it in any transistor, FET, IC, it will demodulate. So you have to do something about this. Now, this kind of interference is common mode. That means that the current, the interference current, runs in the same direction on all wires. So if this is a 5-wire connection, then the current will go in the same direction on all 5 wires. Now, in this case, it's a 2-wire connection. So that interference comes in here on this wire and on this wire. And well, the good thing to do is simply short it to ground. And then at least it cannot get into your load of your IC. So this is the audio input. There will be transistors, FETs, whatever on this side, and you shouldn't have this high frequency there. So simple solution is ground it. Now, the guy who designed this was aware of this, and he thought, okay, I'm going to put the interference on a separate ground plane so it cannot get onto my main ground plane. And of course, they have to be connected somewhere, but since he wanted to keep the interference away, he placed the connection between those two grounds as far away from this signal trace as possible. Now, this is exactly the wrong way to do, and I think some of you may already realize why, because the return current, so the interference comes in here, goes through this capacitor, so that's this one, for instance. It has to go all the way around like this. And the other one has to go all the way around like this. Now, we just discussed and demonstrated that loops are inductors and they transmit, they give impedance, all kinds of trouble. So what you really got is this. You added 3 inductors. Now, this is a very rough schematic way of presenting it. So this would be L4. So this one, the first one. And then you have one path like this, path like this. So that's these two. So that meant that this interference that they were subjecting this thing to simply got through at a number of frequencies. So a colleague of mine came walking in with this board. He said, shit, I've got audio breakthrough. And I looked at it. I said, oh, this looks very suspicious. So what did I do?
I will guess.
Yeah.
You shorted it just under the signals.
Yeah, because then the return path is very short. It's exactly what I did. Luckily, this ground was available at the bottom. So this was literally a 5-minute fix. He went back, he measured it, problem was gone. And what you reality are doing is you're removing these 3 inductors. And yeah, this shows the incredible power of this knowledge and applying this. The bad thing is someone, this was an example in one of my YouTube movies, and someone mentioned, hey, I got an EMC guide from a supplier and they're actually showing this as a solution. I didn't ask the guy which supplier that was because it would be nice to actually download that document and show it. But this is really wrong. And you're violating the rule here that you always should have a single ground plane, which is unobstructed. And we basically have an obstruction here. It's just like that trace that we showed in the beginning, which had an obstruction under it. This is the exact same thing. But now you see a practical application where actually you're failing EMC regulations. So yeah, I thought this was a really nice one.
Okay, I'm going to add my own experience with this. I have 2. So first one was very similar to this one. We had EMC problems, but it was at the time when I was very young and I was like reading all these data sheets which were saying you have to split grounds. So I created analog ground for audio part and digital ground for the digital part. And there was this senior engineer and he told me, don't do it like this because it will not work. So I was like, okay, I'm going to do experiment. So I placed 0 ohm resistors all around, footprints for 0 ohm resistors, and you know what happened? So we measured EMC, and when it was connected only in one point through one 0 ohm resistor, failed EMC. When we connected everything as like solid ground plane, passed everything.
Great.
So yeah, this was one example. And I did it because I really was worried exactly what we are talking about. There is the analog sensitive circuit and then digital noise from processor and everything is going to go to this analog circuit. No, that's not true. You can use solid ground plane. We will talk about this a little bit later, but it will work fine if you do placement correctly and if you do layout correctly, then digital will stay in digital part, analog will stay in the analog part. The second example was with failing ESD test. So it was not like this. They actually recommended to place a ferrite bead between these two ground planes, and it always discharged through the chip, and it damaged the chip.
Of course.
Solution was use 0 ohm resistor, but the best would be just don't separate the grounds, just make solid ground plane.
Yeah, there's only one reason why you should separate ground. That's when you have an actual galvanic separation, like an AC DC supply or something. But other than that,
maybe there are some examples. I don't know, maybe when you are designing very sensitive devices or something, but for digital boards, what I normally design, I never had problems with solid ground plane. Even I need to say I had like digital parts on the top of the board and analog parts on the bottom. It was 12-layer PCB, of course, so everyone had its own kind of ground under the signal, so they didn't mix together or anything. It was working perfectly fine.
Yeah, I can imagine. Yeah.
Okay, so what do you have on the next slide?
Well, this is something from my hobby. I've been designing high-end audio equipment since I was 19. Of course, when I was 19, it wasn't so high-end yet. But anyway, this is the most advanced piece of equipment I've made. And it's a DA converter. And I have a FPGA board here, which does a lot of digital signal processing. And I started off this design with an off-the-shelf FPGA board because I hoped that that would be good enough. Turned out to be not a good idea. So this was the spectrum. I zoomed it in a little bit with the off-the-shelf board. And this was the spectrum with the board you see on the right that I designed myself.
So you redesigned the board which you planned to buy.
Yeah. And I thought, FPGA board. You know, it's a piece of cake. It's going to be a few days of work and then I have it. That actually turned out into a number of weeks. And the reason was that I did not want to resort to very expensive board technology. You know, if you have 6 or 8 layers and micro vias, making a board like this in the right way is a piece of cake, really. Unless you want to connect every little I/O, then you still have to be careful. But I wanted to stick to 4 layers with standard through-hole vias. And so I finished the layout. And then I thought, how much power drop would I get on these traces? So I did a calculation and I thought, okay, it's very wise that I did that because I had way too much voltage drop. And then it was a real headache trying to get enough copper for the ground, enough copper for the supply, and not ruin the EMC performance. But yeah, as you can see, I made the right trade-offs using all these rules that we've just been talking about. And this was really the first board. I'm still using it 5 years later, and you can see it's perfect. I mean, this is another plot of the spectrum. Here you see a little bit 50 and 150 hertz. That's the grid. That's 220 volts grid, so you'll always have that. It's very hard to keep that out. Here you see the 1 kilohertz. You see a little bit of distortion, but it's well within spec. Look, minus 110 decibels, and for the rest, it's completely clean. So that's a nice demonstration of, this off-the-shelf stuff, it's very often not designed for EMC. If you also just look at the connector, they use a ground connection every 20 pins or something, or 30 pins. So the return path there will always create large loops. So yeah.
I created video on this topic. It's not out, but maybe it will be out when we publish this video. So I will link it. I will link it.
Okay.
Because it's still on my hard drive, and it's with Eric Bogatin, and we were actually talking about these, how many ground pins we should place on connector.
Yeah, exactly.
Okay, and I think that's the last slide, is it?
Let me think.
Oh no, we didn't talk. No, there is more. There is more.
Star grounding.
And 34. What is 34? We had 34.
Yeah, we had that one already. Yeah. So I made one video about common bad advice. We already discussed the split ground planes, which I keep finding in data sheets. It's amazing. And the other one, which is very persistent, is star grounding. And I never understood where it came from until I made this video on YouTube, because someone in the comments said, yeah, well, this basically comes from the old days when they were making tube stuff and things like that. They didn't have boards usually. And then star grounding was a really good idea because you couldn't make planes. So the next best thing then is a star ground. But the problem with star ground is, and I'm demonstrating that on this same filter. So I made a star ground layout like this. I actually didn't build this. I just drew this for demonstration purposes. And yeah, a few things are happening. First of all, these traces have inductance. So you will have a lot of inductance. We already saw the impact of a via, which is a few picohenries. Well, this is going to be like 16 to 25 nanohenries. So that's a complete disaster compared to those other numbers. And the other thing is you have a loop here, basically, but you also have a loop here. And these loops are inside of each other. So you're going to create huge crosstalk. There's a whole bunch of transformers here, unwanted transformers, which are completely going to ruin the performance. And yeah, so if you were to live in a Faraday cage and you have a really low frequency application and no interference, no Wi-Fi, no GSM, none of that, then a star ground will probably work fine. But as soon as you get to an environment, a real life environment, and a little bit higher frequencies, then it really will not work anymore. Let's see, did I say, yeah, plane? Oh yeah, here I'm explaining the difference between a plane. We already went through that a little bit. I basically just explained that the return forward path is here and the return path is right under there. So you create very small loops versus this case where you create very big loops which are transmitting and interfering with each other.
Okay. And the next one?
Yeah. And this is your example, the multiple ground planes again. Yeah, so I just wanted to show how this works fundamentally. So we have a digital domain and an analog domain, and we have some signal going between these two. And so the advice is split it. And very often the advice is as well, connect them as far away as possible at the analog and digital transformer,
or
for
under
instance.
The chip.
Huh? What?
Under the chip.
Yeah, that will work as well, but yeah, only for return currents under the chip.
Yeah.
So yeah, if you have two chips, what do you do then? I mean, if you have a stereo DA converter, you have two of those DA converter chips. Yeah, what's your start point then? Or how do you do that? You're supposed to connect them in one place. So you immediately get into that puzzle in your head. But in any case, so let's see what happens during this situation. So if the signal goes here, then the return current will have to go all the way around. Now, we've clearly established that's not a good idea. So what do you get in practice? You get this inductor. And this has very big implications because this ground will now have a different potential than this ground. There will be RF signal on there. The other thing is that the power supply is AC coupled to this ground. So the power supply also has the same potential potential difference with respect to the power supply on this side. So what you've actually done is you have added the interference that you try to prevent right on top of your signal. So you got to get your head around this. You try to prevent something, but you actually caused it to become the worst possible you could achieve. And that is why you should never use multiple ground planes. Okay, I got you totally silent.
No. Oh,
Well, that was basically
like,
the end of my argument, I think.
No. I was only thinking like what I mentioned before. Maybe there are some special cases when you need multiple ground case. So I would not say like never ever, but generally,
there is a situation where
you would like to make antenna.
Yeah, when you make an antenna, of course. Yeah, that's one of them. But there's also signal reasons. For instance, if you make if you make a power amplifier, then you can imagine that the output stage runs very, very high currents. And even through a plane, that will cause very tiny voltages. Now, if that amplifier has a distortion of minus 110 decibel, that means that the signal on your ground has to be lower, 110 decibels lower than your signal that comes out of your amplifier. Now, that's a hell of a lot. I mean, that's 300,000, I think. So there you actually have to be careful. And what I usually do, I make a virtual ground planes or ground point, star point, somewhere in my plane. That's also where my loudspeaker connector is. I put the high currents on the right of it. So that's the output stage and all the currents running there, and my input circuitry on the left. And then you've basically prevented, without damaging your plane, that the voltage created by the huge currents of your output stage start mixing with the reference ground on your input stage. So this is one example where if you don't pay attention, even a single ground plane won't save you. But you're talking very often about high current, high dynamic range circuits on the same board. And a power amplifier is a great example of that. I think if you build a 9-digit multimeter, you may also run into stuff like this. Because, then you're also looking at an insane dynamic range.
Mm-hmm. Okay, that's good to point this out.
What?
That's good to point this out.
Yeah.
Like, because then people will be like, I followed your video and it doesn't work.
Exactly.
You are building the special case.
Yeah. You know, the thing is, this is actually difficult because when you're trying to explain things like this on YouTube, it's very hard sometimes to see how far you go because these are exceptions which are relatively rare, and you make much more gain by following these three main rules that we're presenting here than by violating them.
Yeah.
So the general thing should always be make a single ground plane. But the reason why I try to explain all the underlying theory is that you can think for yourself.
Mm-hmm.
And if you have an output power amplifier that runs 10 amps and you have an in through the ground and you have an input, then you should think, okay, wait a second, I may get some voltage drop. If it gets to my input, I'm in trouble. So now I have to pay attention. So these rules will cover 95% of situations and get you the best result. Maybe even more than 95%, but it's very important that you keep thinking and that you actually understand what's going on. That'll really make you an outstanding electronic engineer, in my view. Mm-hmm. At least all the engineers that I really look up to do this. So
I agree. I would like to mention that even high current, it doesn't have to be always problem, because also motherboards, they can have tens or even hundreds of amps in this digital part, but then key is you place the power supplies extremely close to the power pins, so it doesn't spread all over the board or something. Yeah,
exactly. That's also what you do by doing that is also keeping the loops as small as possible.
But it would not, if you place it far away, it would not work.
Yeah, exactly. Yeah, because I think even the DC resistance would kill the application in this case, even if you use multiple layers and planes to conduct power.
Yeah, definitely. Okay, you have a last example.
Yeah, so this is another one example of the argument, but if I have analog and digital on a single board, I need to use separate ground planes. Now, this is the DA converter I just showed. This is the bare board, basically. And what you see, this block here on the left is my digital part. This is the left part, and this is the right part, or the other way around. I don't know. What we've just shown is that
it says right and left.
Yeah, right block and the left block. So what we've just shown is that return currents will always be under the traces. So that means that all the currents related to left,
it's working again,
will stay under this block. All the currents related to right will stay under this block, and anything related to digital will stay under this block. Well, if those currents stay under their own blocks, then they will not interfere with each other, unless you come to the idea that I have to put this FPGA in the middle of the analog. Yeah, then it'll go wrong. But if you separate your digital and analog parts in separate blocks, there is no way they're going to interfere with each other on a single plane, because the currents simply don't mix.
Yeah, that's also, you need to be careful how you place, for example, power supplies and these things, because that's what could cross multiple.
Yes, exactly. Yeah, so you don't want to run the digital supply from this connector all the way under here to over there. It has to come from, well, at least here.
Yeah. Okay.
Actually, in this design, all the power comes in here, but the traces are running here. So the return currents will stay nicely away from the analog part.
Thank you so much, Hans, because I love the examples. It was so cool. And I like making these kind of practical videos. Thank you very much for sharing this.
Yeah, you're welcome. I really enjoyed it as well.
Okay, so if someone would like to learn more, you have very cool videos. You have very cool YouTube channel, so people can follow
exactly.
you.
Yeah, I started a few months ago only, and it really took off. People are so enthusiastic, and I really like that. And the reason why I do this is I would love to earn a living with electronics, and it's a little bit difficult in Holland. There's not that many electronics companies, so I want to try to sell my 42 years of experience in electronics. I started when I was 8. So I'm currently working on this, which is an electronic product development course. And what I want to do is show people how they can turn this conceptual schematic, which is basically a signal generator with an FPGA, DA converter, low noise, crystal oscillator, amplifier, how you turn such a conceptual schematic into a full board with all these rules. These grounding rules will be part of it, but I will go over EMC, ESD, component choices. Why do you need an NP0 capacitor? Why an X7R? Why a certain type of inductor? Why not the other? Why do you need an LDO here? And what would you need to do to get this thing ESD resistant, EMC resistant? So everything I've learned in all that time, I would like to put that in a single course. And so that's what I hope to make a living with. And YouTube is a nice way to show people, hopefully, that I know something and it could be valuable to them.
And you do also freelancing? So do you do also some custom consultation, or what do you do?
I'm probably going to do something for a company in Luxembourg. They also found me through this and they wanted some help. At the moment, I am available, but at the same time, I'm working really hard on this course. It's going to take me 3 months to build, I think, because of all the detail I want to put in.
Multiply by 2, at least. Always.
What? Multiply by 2. Yeah, I hope not. I already did that, so I hope it doesn't become multiply by 4. But yeah, I really want to try to get all my knowledge across. That would be really cool if I managed to do that, because then this is worth a lot of money in a professional environment. So yeah, fingers crossed that I can do this, because it's very scary. I left my job basically and went to this, and I'm very happy with the way it's going now. And I'm very happy that you invite me, because it's very nice of you. And hopefully I can make a living teaching people electronics and how to be better engineers. That would be fantastic.
Do you have some kind of form where people can sign up and you would notify them when the course
Yeah, well,
is...
basically this page, I have a pre-registration form.
Oh, okay.
So yeah, it's going pretty well. I've had it up for a few weeks and I have 50 pre-registrations already. Now, I don't know if these people are actually going to buy, because you don't have to pay to register, but because I don't want to hold on to people's money for months and months and months, as long as I'm making this course.
Yeah, I understand.
But you can pre-register, or yeah, something else. I have a free. Why is it not working? Oh, it's a bit slow. I made a 15-page document where I have the whole curriculum of my course, basically. So what components to choose, schematic checks, PCB checks, reliability, all kinds of stuff. Lots of value here, and it's completely free. And if you leave your email, you get this thing, and I'll also keep up to date there about my course. Now I've been having this list for 2.5 months, or no, it's longer. I've had this list for 4 months, and I've sent 1 email, so I'm not spamming a lot. But if my course is ready, I will be spamming you guys.
Okay, so if anyone is interested, they can go on your website and sign up, give you some feedback. That's always useful. Okay.
Yeah, and it's so nice, the feedback that I got on this document. The nicest feedback were from some engineers that also had been doing this their whole life, and they read it and they said, yeah, this is great. It's a really good summary of all the things that can go wrong and that you have to take care of. So yeah, it has been really nice until now. And
I love you build all these examples, because not everyone will build examples, and the real life examples are very eye-opening, and it helps a lot.
Yeah, it's because I don't believe anything until I really see it. Just like you said with those 0-ohm resistors, you thought, okay, I have to really see it. And it's a bit annoying because therefore I learn slower, but when I learn, I really know for 100% sure that it's true, That's an advantage.
Yeah, exactly. Okay, thank you so much, Hans.
Yeah, thank you.
So if people have any questions, they can leave them in comments, and if they have any other ideas on the video, what we could talk together, also they can leave in comments. Thank you. Yeah. Thank you very much, Hans.
Okay, bye.
Thank you. Bye. And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FedDevel online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments, and see you next time. Bye.